Welcome to Global Virtual School. Students, this is your first year chemistry class. I am Dr. Jadmanu, and the topic for today's discussion from chapter 4 is but are absolute temperature scale, relationship between temperature and average kinetic energy of the gases, and the gas pressure in the light of kinetic molecular theory. Students, we will discuss in today's lecture just what is absolute temperature scale and relationship between temperature and the average kinetic energy of the gas molecules. We will also discuss with reference to liquids and solids and the gas pressure in the light of kinetic molecular theory. And after completing this topic, so you will be able to know what is actually this is absolute temperature scale, and you will be able to interconvert all the temperature scales like Celsius, Fahrenheit and Kelvin, that is called absolute temperature scale. And you will be able to relate the temperature on the base of average kinetic energy of the particles in a substance, how this average kinetic energy actually measure the temperature of the substance. So just recall you about the thermometric scale. You are quite familiar about the Celsius scale and the Fahrenheit scale, and a third one, that is the Kelvin scale. First, Celsius scale, you know this it's represented by a C naught. And wherever this C naught, it means this is the temperature, and this temperature is in Celsius. And I will tell you with reference to the that is water, ice or liquid. You know, water has H2O has three states, like solid. Solid is like ice, liquid, that is water, and the gas, that is the steam. And you know, with reference to these, you know, when there is 0 Celsius and 100 Celsius, at this temperature 100 Celsius, and at the 0, between 0 and 100 there are 100 deviants, and at this temperature this is in the form of liquid, and as it convert at reach 0 and it start converting into solid. Below this is the solid form, and at 100 it start converting into its vapor, that is called steam, and this is the gaseous state. So between 0 and 100 there are 100 deviants. While Fahrenheit scale, this start with reference to this, it's when this is 0 Celsius, then Fahrenheit Celsius at this state, this is 32 Fahrenheit, and when it is 100, then it is 212 Fahrenheit, means their deviants are 180. So it gives even a more accurate temperature scale. And the third one is absolute temperature scale, that is Kelvin. When this is 0, then in Kelvin this is 273 Kelvin, and when it is 100 Celsius, then this is 373 Kelvin. It means this also has 100 deviants, 100 parts. But why they start from 273 we'll discuss in later, and how this can be convert this Celsius into Fahrenheit, Fahrenheit into Kelvin. We have different formulas. First, if you have Fahrenheit temperature, when it is Fahrenheit, it means this is the temperature. Keep the Fahrenheit temperature here, 32 and minus 32, and there is 5 by 9 out of the bracket. So solve this, then this Fahrenheit temperature will be converted into Celsius scale. And how you can convert the Celsius into Fahrenheit? Keep the Celsius scale here and convert the Fahrenheit with the help of this formula. You can easily find out. And how you can convert the Celsius into absolute temperature? And this can be solved with the help of when you add 273.16 in Celsius temperature. So C naught means temperature in Celsius. Whenever you add 273.16 in Celsius scale, then this is equal to the Kelvin. Now I will tell you how what is this absolute temperature scale or Kelvin scale on the basis of Charles' law. Why we use this absolute Kelvin scale, although they have the same deviant as the Celsius scale deviant. First, focus on, according to Charles' law, at a constant pressure, the volume of a given mass of a gas increases or decreases by 1 over 273 of its original volume at 0 degree for each 1 degree rise or fall in temperature. You know, for 1 degree rise, volume increase. fall in temperature, 1 degree fall in temperature, temperature decreases. How much decreases? 1 over 273, or you can say 273rd part. 273rd part of original volume. Original volume can any be original volume. It can be 100 centimeter cube. It can be 500. It can be 1000. Any. But the original volume that is at 0 degree, that's 273rd part increases with each 1 degree rise, and it decreases with each 1 degree decrease in the temperature. And if we start keeping the temperature decrease, then its volume becomes 0 at minus 273. Point more accurately at minus 273.16 Celsius. So basically this minus 273.15 or 16, this is unattainable temperature, and gas is converted into liquid or solid before it reaching this temperature. So this is called absolute absolute zero temperature. And the Lord Kelvin, he succeeded in measuring the temperature of the gas with the help of new scale. So at this point he devised a new scale. As at minus 273, gas volume becomes 0. So he said, how much I add into this that it is equal to 0. Of course, when you add 273, then this is equal to 0. Then this is called the Kelvin scale. So if we add to the Celsius scale a value plus 273, then the Celsius is converted into the Kelvin scale. So when there is 0 Celsius, then Kelvin scale is 273. So Kelvin scale or absolute temperature scale is when 0 Kelvin then starts at minus 273. So when this is 0 Kelvin, at that point this is the minus 273 Celsius, because minus 278 Celsius plus 273, that is equal to the 0 Kelvin. So 0 Kelvin is when Celsius is minus 273, and when Celsius is 0, then Kelvin is plus 273, and so on. So this is the Kelvin scale. You can convert Celsius into Kelvin and vice versa, means Kelvin into Celsius. So this is very simple formula. You have Celsius temperature, to this add 273, you will convert into the Kelvin. If you have Kelvin, then minus this 273 from Kelvin, you will convert this into Celsius. Now let me have some examples to convert Celsius temperature to Kelvin temperature. First you have given minus 132 Celsius. Very simple, you have the formula. To this add 273.16 or 15 or simply 273. You can find the 141.16 Kelvin. This is the answer. 296 also add 273.16. That is the temperature in Kelvin. To this 0 add 273. Then you can find the temperature in Kelvin, but you have to do it yourself. 2 minus 12 plus 273. Students, be careful about the symbols on the start of this value, either it's the minus or it's the positive. So minus 12 plus 273, what will be the answer? You have to find out. Next is 148 plus 273, then you can find the answer. Now similarly, there is the example, convert the Kelvin scale into the Celsius temperature. So this is like you have to minus the 273.16 from the Kelvin temperature. That is very easy, you can find the answer. So solve the other example C and D by yourself. And now this is the important topic, that relationship between temperature and average kinetic energy of the particles in gas. So you are quite familiar about this, that temperature of the gas depends upon the kinetic energy of the molecules. If some gas molecules, they have higher kinetic energy, it means they are at higher temperature. If they have lower kinetic energy, it means they are at the lower temperature. And how you can drive a relationship, mathematical relationship between kinetic energy and temperature. And this, when a gas is at some state, at some particular temperature, as you will increase its temperature, its kinetic energy will change and will redistribute. as you decrease the temperature, again its kinetic energy will be changed and redistributed. So according to kinetic gas equation, P equals to 1 by 3 mc square and kinetic energy is equal to 1 by 2 mc square bar. And now this is the right side of the kinetic gas equation. If you multiply this equation, right side of equation, and divide this equation will remain same because 2 cancel by 2. But in this way we will rearrange and we interpret this in terms of its kinetic energy in this way. So on the right side of equation, multiply with 2 and divide by 2 and then rearrange. This is just rearrangement of this equation, like this is 2, here 2, 3, this one is n, and we have put the mc square and this division that is divided to in a bracket because this is equal to the kinetic energy. So make this equal to kinetic energy because half mc square bar is kinetic energy, and this is for n is the number of particles, and if we have 1 mole of gas, and you know that is equals to Na that is the Avogadro's number, that is for 1 mole. So instead of n we will write Na, and you have this is the equation like P equals to 2 by 3 Na into kinetic energy equation 1. And you know the general gas equation or ideal gas equation, that is P equals to nRT, and because this is P equals to nRT and in the previous that is also P equals to, so and if we take this for 1 mole, if this is the number of molecules and is for 1 mole, keeping this one, this equation will be P equals to RT. Now if you compare equation 1 and equation 2, then you have this equation. Now keep the kinetic energy on this side and take all the values to the other side of the equation. So Na will be divided towards, 3 will be multiplied and 2 will divide on the other side. So we have kinetic energy equals to 3 RT, 2 divided and Na is also divided. And in this equation you can see 3 is constant because it's a number, 2 is constant, Na is 1 mole, number of moles of gas are constant, R is already ideal gas constant, and now temperature is variable, temperature can be it changes. So you can see these are values, these are constants. It means kinetic energy is direct proportion to temperature. So what we conclude is that Kelvin temperature, that is this temperature of a gas, is actually the measure of average translational kinetic energy of the molecules. But translational kinetic energy only in case of gases and liquid, and you know in gases I already told you in motion of particles, gas molecules, they travel in a straight line, they have translational motion. Liquids also travel in a straight line until unless they collide with one another or with the walls of the container, they travel just in a straight line. So in gas and liquids, temperature explains the average translational kinetic energy of the molecules, while in solids, because solids molecules are not free to move, they have vibrational motion, so the temperature explains the average vibrational kinetic energy of the molecules in case of solids. So the question can be asked like, relate temperature to the average kinetic energy of the particles in a substance, or kinetically how will you interpret the effect of temperature on gaseous molecules. These two questions are same, and what is the answer? We have just discussed this, the relationship between average kinetic energy or temperature and average kinetic energy of the molecules in a substance. So you have to go for it. What is the gas pressure? You know, pressure is the force per unit area, but in the light of kinetic molecular theory, first you know the postulate of kinetic molecular theory, what it says. Gas molecules are in a constant state of random motion, constant state of motion, random, just they move in x-axis, y-axis or z-axis in a straight line. They move in a straight line until unless they collide with one another and with the walls of the container in which the gas molecule is present, either it's in the like balloon or some other container. So pressure exerted when gas molecules they collide on the walls of the container. And you know, if every kinetic energy is responsible for the movement or the kinetic energy of the gas molecules. If the temperature is same, then they have the same pressure. But as the temperature varies, temperature rises, its collision increases. So its force on the area that they are exerting increases. If you decrease the temperature, then the collision decreases, and the force with which they collide on the walls of the container, it decreases. So pressure defined as force being exerted over a unit area is called pressure, or simply you can say the force per unit area. Mathematically we write it pressure is equal to, this one is the pressure, F is the force, and A is the area, force per unit area. So what will be the units of pressure? Of course, units of force and units of area. That is system international, that is as standard international units जो है standard international units of pressure is Pascal, that is PA. This is on the name of scientist, and the SI unit for force is Newton, and for area is the meter square. So the unit will be Newton per meter square, and we can also say the Pascal, but this is a smaller unit as compared to another unit, that is atmosphere, and 1 atmosphere is equal to 101325 Pascal, or you can say, because Pascal and Newton per meter square are same, that is 101325 Newton per meter square. So this is the relation between atmosphere and Pascal. And there is one other unit that is called pounds per square inch. So 1 atmosphere is equal to 14.7 pounds square inch. And Pascal, and what is the difference between Pascal and kilopascal? Obviously kilopascal is greater. So when Pascal equals 1000 Pascal is equal to 1 kilopascal. So divide this by 1000, then you will got 101.325 kilopascal, that is equal to then 1 atmosphere. And there is another unit that is called torr, or millimeter of mercury. Torr is again on the name of scientist, and this is millimeter of mercury. And the atmosphere is greater unit as compared to torr or millimeter of mercury, that is 760 millimeter of mercury is equal to 1 atmosphere. And if you know 1 Newton meter is equal to 1 joule, and 1 joule equals to 10 + 7 ERGs, and that is equal to kilogram meter square per second square. And also there is larger than joule is the calorie. 1 calorie is equal to 4.184 joule. And in this way there is and also other unit that is called the bar, and bar is again a lesser unit, smaller unit than atmosphere. 1 atmosphere is equal to 1.01325 bar. So these all are the units of the pressure and system international units. And this is the Pascal and Newton meter, but atmosphere is the standard unit. So now we have the example, convert 10 Pascal into kilopascal. Obviously you can find Pascal and kilopascal. 1000 Pascal is equal to 1 kilopascal, then 10 Pascal will be equal to 10 over 1000. So this is converted into kilo. So convert Pascal into atmosphere. You must know the relation. 1 atmosphere is equal to 101325 Pascal. You can say 10 Pascal will be equal to 1 over 101325 into 10, and this is the 0.098 atmosphere. The question from your exercise are define pressure. So we have just discussed how to define the pressure and their units. And then question is, how will you explain the gas pressure with the help of kinetic molecular theory? We have just discussed in 3-4 statements that gas pressure is according to kinetic molecular theory. And so this was all about today's, that is absolute temperature scale, and the relationship between temperature and every kinetic energy of the gases and the gas pressure in the view of the kinetic molecular theory. Our next topic will be Boyle's law, that is important topic. Boyle's law, you can also say this is the discussion on the effect of change in pressure on the volume of the gas.